In this video, the following topics will be covered: cluster analysis, overview of different categories, applications of cluster analysis, types of data in cluster analysis. Unlike in classification, the class label of each customer is unknown. We need to discover these groupings. Given a large number of customers and many attributes describing customer profiles, it is very costly to have a human study the data manually. So we need the customers into strategy groups. So for this purpose, we need a clustering. So clustering is a process of grouping a set of data objects into multiple groups or clusters so that objects within a cluster have high similarity but are very dissimilar to objects in other clusters. Dissimilarities and similarities are computed based on the attribute values describing the objects and often involve distant measures. Clustering as data mining tool has its roots in different applications areas such as biology, security, business intelligence, and web search. In machine learning, recall that classification is known as supervised learning because the class label information is given. That is, the learning algorithm is supervised in that it is told as the class membership of each training tuple. Clustering is known as unsupervised learning because the class label of information is not present. For this reason, clustering is a form of learning by observation rather than learning by examples. Applications of cluster analysis. Biology is one of the major applications for clustering process. Second, information retrieval. In this, document clustering can be done. Third one, land use, identification of areas of similar land use in an Earth observation database. Fourth one, marketing, which helps the marketers discover the different groups in their customer bases and then use this knowledge to develop targeted marketing program. Fifth one, city planning, identifying the groups of houses according to their house type, value, and geographical location. Sixth one, earthquake studies, observed earthquake epicenters should be clustered along continent faults. Seventh one, climate, understanding Earth climate and finding the patterns of atmospheric and motion. Eighth one, economic science, it is used for market research. Ninth one, owing to the huge amounts of data collected in databases, cluster analysis has recently become a major process. Last one, it's a highly active topic in data mining research. What is good clustering? A good clustering method will produce high quality clusters. High quality cluster means high intra-class similarity and the low interclass similarity within the interclass similarity between the cluster. The quality of a clustering method depends on the similarity measure used by the method and its implementation and its ability to discover some or all of the hidden patterns. Measure the quality of clustering. Dissimilarity and similarity metric. Similarity is expressed in terms of a distance function, typically metric distance between I and j. The definitions of distance functions are usually rather different for interval scaled variables, Boolean variables, categorical variables, ordinal ratio, and vector variables. Weight should be associated with the different variables based on applications and semantics. The quality of a clustering means there is usually a separate quality function that measures the goodness of a cluster. It is very difficult to define the similar enough or good enough. The answer is typically high subjective. Based clustering. Real world applications may need to perform clustering under various constraints. Suppose that your job is to choose the locations for a given number of new automatic teller machines in a city. To decide upon this, you may cluster households while considering constraints such as the city's rivers and highway networks and the types of and number of customers as per the cluster. A challenging task is to find a data group with good clustering behavior that specifies specified constraints. Next one, interpretability and usability. Users want clustering results to be interpretable, comprehensible, and usable. That is, clustering may need to be tied in with specific semantic interpretations and application. So it is important to study how an application goal may influence the selection of clustering features and clustering methods. Data matrix. The structure stores the n data objects in the form of relational tables, n by p matrix, as shown in the screen. Each row corresponds to an object. As part of our notation, we may use the F to index through the p attributes. Second one, dissimilarity matrix, object by object structure. The structure stores a collection of proximities that are available for all pairs of n objects. It is often represented by a n by n table, where d of I, j is the measured dissimilarity or difference between the objects I and j. In general, d of I, j is a non-negative number that is close to 0 when objects I and j are highly similar or near to each other, and becomes larger the more they differ. Note that d of I equals to 0, the difference between an object and itself is 0. Furthermore, d of I, j and d of j, I, for readability purpose addition, we do not which measures the dissimilarity are discussed throughout the remainder of this video. The d of I, j measures the similarity, and dissimilarity can often be expressed as a function of measures the similarity between the two objects, where SIM, similarity of I, j is the similarity between the objects I and j. Thus, the data matrix is defined as a two-mode matrix, deals with the different entities. Dissimilarity matrix is known as a one-mode matrix, it deals with the same entity. Different types of data in cluster analysis. Number one, interval scaled variables. Second, binary variables, nominal, ordinal, and ratio variables. Then variables of mixed data. Interval scaled variables. Interval scaled variables are continuous measurements of a roughly linear scale. Examples are weight and height. The measurement unit used can affect the clustering analysis. For example, in a changing environment, units from meters to inches for height or from kilograms to pounds for weight may lead to a very different clustering structure. To avoid the dependence on the choice of measurement unit, the data should be standardized. Standardizing measurements attempts to give all variables an equal weight. So data transformation by normalization, the measurement unit used can affect the data analysis. To standardize the measurements, one choice is to convert the original measurements to unitless variables. Three different distance measures are available. Distances are normally used to measure the similarity or dissimilarity between the data objects. Some popular one is the Minkowski distance, second one Manhattan distance, and third one is the Euclidean distance. Standardization in certain applications, the dissimilarity between the objects described by interval scaled variables is typically computed based on the distance between each pair of objects. The most popular distance measure is Euclidean distance. Another well-known metric is Manhattan distance. Euclidean distance and Manhattan distance satisfy the following mathematical requirements of a distance function. D of I, j greater than or equal to 0 is distance is a non-negative number. D of I, equals to 0 is the distance of an object to itself is 0. D of I, j equals to D of j, I is distance is a symmetric function. D of I, j less than or equal to D of I, h plus D of h, j is going directly from object I to object j in space, no more than making a detour over any other object h. That's a triangular inequality. Screen, Minkowski distance and Euclidean distance formula has been given on the screen. Minkowski distance is a generalization of both Euclidean distance and Manhattan distance. It is defined as d of I, j equals to x of I1 and j of x of j1 up to the last term. Euclidean distance when p equals to 2, that also has been, the formula has been given on the screen. In the screen, the scatter plot is used to represent the values of the attribute 1, attribute 2. The x1, x2, x3, x4, and the attribute 1 value, attribute 2 values are shown on the screen. For x1, attribute 1 value is 1, attribute 2 value is 2, Likewise, for point x2, attribute value 1 is 3 and attribute 2 value is 5. So this is plotted as a dot scatter plot on the graph. Manhattan distance and Euclidean distance are calculated. That is given. That is tabulated. That values are shown on the graph. To compute the dissimilarity between the object described either for binary variables. Dissimilarity and similarity measures for objects described either symmetric or asymmetric binary attributes. So how to compute the dissimilarity between the two binary attributes? We can have an approach involves computing a dissimilarity matrix from the given binary data. If all binary attributes are thought of as having the same weight, we have the 2 by 2 contingency table as shown on the screen, where Q is a number of attributes that equal 1 for both objects I and j. R is the number of attributes that equal 1 for objects I but equal 0 for object j. S is the number of attributes that equal 0 for object I but equal 1 for object j. And T is the number of attributes that equal 0 for both objects I and j. The total number of attributes is P, where P equals to Q plus R plus S plus T. Recall that symmetric binary attribute, each state is equally valuable. Dissimilarity, that is based on the symmetric binary attributes, is called a symmetric binary dissimilarity. If objects I and j are described by symmetric binary attribute, then the dissimilarity between I and j can be defined as d of I comma j equals sign r plus s divided by the q plus r plus s plus t. For asymmetric binary attribute, two states are not equally important, such as the positive or negative. The outcomes of a disease test. Given two asymmetric binary attributes, the agreement of two ones is then considered more significant than of two zeros. Therefore, such binary attributes are considered monary. The dissimilarity based on these attributes are called asymmetric binary dissimilarity, where the number of negative matches also can be shown, but it is unimportant. In the contingency table shown on the screen, the contingency table for binary data has been shown. The distance measures for symmetric binary variables has been given. D of I comma j equals in b plus c divided by a plus b plus c plus d. Distance measure for asymmetric variables also has been given. D of I comma j equals sin b plus c divided by a plus b plus c. Jaccard coefficient, that is similarity measure for asymmetric binary variable. Similarity of I comma j equals to 1 minus d of I comma j. Total number of binary variables is p, where p equals in q plus r plus s plus t. The binary variable is symmetric if both of its states are equally valuable and carry the same weight. There is no preference on which outcome should be coded as 0 or 1. Dissimilarity that is based on symmetric binary variables is called symmetric binary dissimilarity. A binary variable is asymmetric if the outcomes of the states are not equally important, such as the positive and negative outcomes of a disease test. A binary variable contains two possible outcomes, 1 or 0. If there is no preference for which outcome should be coded as 0 or which one, the binary variable is called symmetric. For example, the binary variable is evergreen. For a plant as a possible state loses leaves in winter and does not lose leaves in winter. Both are equally valuable and carry the same weight when a proximity measure is computed. If the outcome of a binary variable are not equally important, the binary variable is called asymmetric. An example of such a variable is the presence or absence of a relatively rare attribute, such as color blind for a human being. While we say that two people who are colorblind have something in common, we cannot say that people who are not colorblind have something in common. Coefficient, the number of negative matches T is considered unimportant and this is ignored in the computation as similarity of I comma j q divided by q plus r plus s. equals to 1 minus d of I comma j. We can measure the distance between two binary variables based on the notion of similarity instead of dissimilarity. The coefficient of similarity of I comma j is called the Jaccard coefficient. Suppose that a patient record table shown on the screen contains attributes name, gender, fever, cough, test 1, test 2, test 3, and test 4, where name is an object identifier, gender is a symmetric attribute, and the remaining attributes are asymmetric binary. For asymmetric attribute values, let the values y and the means yes and p means positive be set to 1 and the value n for to be set as 0. Suppose the distance between objects is computed based only on the asymmetric attributes. As per the equation shown on the screen, it can be calculated as distance between the Jack and Mary, distance between the Jack and Jim, and distance between the Jim and Mary also can be calculated. The result is 0.33 and 0.67 and 0.75. These measurements suggest that Jim and Mary are unlikely to have a similar disease because they have the highest dissimilarity value among the three pairs. Of the three patients, Jack and Mary are most likely to have a similar disease. Data table and the contingency tables are shown on the screen. Contingency table for binary data and distance measure for symmetric binary variable and distance measure for asymmetric binary variable and Jaccard coefficient also can be calculated as per the formula. A categorical variable is a generalization of the binary variable in that it can take more than two states. For example, map color is a categorical variable that may have say 5 states: red, yellow, green, pink and blue. Let the number of states of a categorical variable be m. The states can be denoted by letters, symbols or set of integers such as 1, 2, up to m. The dissimilarity between two objects I and j can be computed based on the ratio the mismatches, where m is the number of matches and the number of variables for which I and j are in the same state, and p is the total number of variables. The formula is shown on the left hand side. To find the distance between the mixed data type that is shown on the screen, the table containing the object identifier and the test 1, test 2, test 3. Test 1 is a categorical data type, test 2 is the ordinal data type, and test 3 is a ratio scale data type. So the distance is calculated, the value of distance is measured, and it has been shown on the screen in the right hand side. So suppose that we have a sample data shown on the above table, except that only the object identifier and the variable test1 are available. Where the test1 is categorical, let's compute the dissimilarity matrix. Ordinal variables. The values of an ordinal variable have a meaningful order or ranking about them, yet the magnitude between successive values is unknown. An example includes the sequence small, medium, large for a size attribute. Ordinal attributes may also be obtained from the discretization of numeric attributes by splitting the value range into a finite number of categories. These categories are organized into ranks. That is, the range of numeric attributes can be mapped to an ordinal attribute f having mf states. The example, the range of an interval scaled attribute in terms of temperature can be organized into the different states like minus 30 to minus 10, minus 10 to positive 10, 10 to 30, representing the categories of the temperature. That is cold temperature, moderate temperature, and the warm temperature. Let M capital M represent the number of possible states that an ordinal attribute can have. In the table shown on the screen, that which accept that the time only the object identifier and the continuous ordinal variable, and the second one test 2 is available. Therefore, the three states for test 2, namely fair, good and excellent is available. That is MF equals to 3. For step 1, if we replace each value for test 2 by its rank, The four objects are assigned the ranks 3, 1, 2, and 3 respectively. Step 2 normalizes the ranking by mapping the rank 1 to 0.0 and rank 2 to 0.5, rank 3 to 1.0. For step 3, we can use, say, Euclidean distance, which results in the following dissimilarity matrix. So, dissimilarity matrix also shown first, and the data table is shown below. Dissimilarity calculation for ordinal variable. There are three states for test 2, namely fair, good, and excellent. That is MF equals sign 3. Step 1. If we replace each value for test 2 by its rank, the four objects are assigned as 3, 1, 2, and 3. Step 2 normalizes the ranking by mapping rank 1 will become 0.0, rank 2 will become 0.5, rank 3 is 1.0. For step 3, we can use, say, the Euclidean distance will result in the following dissimilarity matrix. Is given, we have a questionnaire to ask the level of satisfaction in terms of safety, comfortable, convenient, and proximity for two locations of park, Park A and Park B. Each level of satisfaction has 5 values. -2 equals to very satisfied, -1 is dissatisfied, 0 equals to indifferent, 1 is satisfied, and 2 equals to very satisfied. Suppose the answers of respondent is as the following. Safety, comfortable, convenient, and proximity for Park A and Park B is given below. We want to measure the dissimilarity of Park A and B according to the respondent answer. Original index has been given. It is converted to rank. Rank has been given for all the values, and then normalizing the rank, then we can arrive the. For this problem, we transform the ordinal scale into the ratio scale. Original index I equals to -2 to 2 is ordered and converted into rank R equals to 1 to 5. The highest rank is R equals to 5. Then we normalize the rank into values 0, 1. For instance, in the position 2, we have I equals to -1 converted into rank become R equals to 2. Normalize the rank x equals to 2 minus 1 divided by 5 minus 1 equals to 1 by 4. Using the normalized rank as new value, we have a coordinates for Park A and Park B. The Euclidean distance can be calculated for Park A and Park B, that is shown on the screen. Ratio scaled variable. Ratio scaled variable makes a positive measurement on a non-linear scale such as an exponential scale, where A and B are positive constants and T typically represents time. Example, growth of bacteria population or the decay of a radioactive element. There are three methods to handle the ratio scaled variables for computing the dissimilarity between ratio scaled variables like interval scaled variables. Apply the logarithmic transformation to a ratio scaled variable f having xif for object I by using the formula yif equal to log of xif. The OIF values can be treated as interval value. Treat XIF as continual ordinal data and treat their ranks as interval value. Later two methods are the most effective, although the choice of method used may depend on the given application. The sample data containing variables of mixed data type shown on the screen. The calculation of dissimilarity also shown below on the screen. The dissimilarity between ratio scaled variables. Ratio scaled variable test 3 are available. Let's try a logarithmic transformation. Log of test 3 results in the values 2.65, 1.34, 2.21 and 3.08 for the objects 1 to 4 respectively. Variables of mixed data types. Here also we can find the dissimilarity between the objects I and j. We can compute the dissimilarity between the objects of mixed variable data type. We can approach is to group each kind of variable together, performing a separate cluster analysis for each variable type. A more preferable approach is to process all variable types together, performing a single cluster analysis. Suppose that the dataset contains p variables of mixed data type. The dissimilarity d of I, j between objects I and j is defined as shown on the screen. Calculate the distance between the different mixed data type like interval scale, binary or categorical or ordinal data has been shown on the screen. Apply the logarithmic transformation to its values based on the transformed values of 2.65, 1.34, 2.21 and 3.08 obtained for the objects 1 to 4. Max HXH equals sine 3.08 and minimum value is 1.34. Then normalize the values in the dissimilarity matrix obtained in the given example, dividing each one by 3.08 minus 1.34 equals to 1.74. Now we can use the dissimilarity matrices for the three variables as shown on the screen. Vector objects. There are several ways to define such a similarity function s of x, y to compare the two vectors x and y. The popular way is to define the similarity function as the cosine measure, where x dash is a transportation of vector x, then x is the Euclidean norm of a vector x dash, then y is the Euclidean norm of vector y, and s is essentially the cosine of the angle between the vectors x